Hello again and welcome to a new lecture in which we will discuss the difference between multi-force members and two-force members. And we will do that from the point of view of the internal forces that are generated in these members due to various actions of external forces. So firstly, let's start with straight two-force members, which are the members that are present in a truss. All members in a truss are straight two-force members, and some members in frames and machines. So this is a two-force member that is straight. It's pinned at A and pinned at B. There are no forces acting along AB, and therefore the end reaction forces, let's call them P in this case, will be directed along the member. Now, in order to see what's happening within the member, inside the member, we could cut the member at an arbitrary point along its length, say at C, and then draw the two resulting free body diagrams, like so. So that's point B and point A, and forces P at the end. Now for equilibrium, at C, we will also have the force P, which has to balance the other one at the end of the member, A or B. So you can see that for equilibrium, this force runs also along the member at C. It is internal to the member. You will not see that force unless we cut the member and we draw the free body diagram of either one side or the other side. And again, P is directed along the member and can put the member either in tension or in compression, as it's the case for the members in a truss, for example. And because this force is directed along the member, it is called axial force. Axial force. So axial because it runs along the axis of the member. So again, straight two-force members have axial forces inside them as internal forces. These axial forces are directed along the member, and they are the only forces that are present in straight two-force members. So straight two-force members will have only axial forces inside them and nothing else. Now we are going to look at a different type of member, which is called a multi-force member. A multi-force member is virtually any member that is not a two-force member that is straight. So what I mean by that, well, let's look at this member here. A at the bottom, so there are two forces here, reaction forces, maybe from a pin that was removed at A, some other forces that are applied along the member, like Bx at B, or perhaps at another point, two forces, vertical and horizontal one, Cx and Cy, and maybe there were some other supports at D, maybe another pin. So here we have reaction forces dx and dy. In order to see what's happening inside this member, we can again make an arbitrary cut, for example at point E, and then we will draw the resulting free body diagrams. So this would be member DE and member AC. All we have to do first is to show again the existing forces on these members. So all these forces at A, AX, AY, at B, BX, then CX and CY at C, and of course at D we have dy and dx. And now we have to analyze the equilibrium of either of these two resulting free body diagrams. So if we take member DE, which is simpler, for equilibrium, we will have an axial force P balancing dy, and we will see this P with an opposite sign on the other side of the free body diagram. Now dx must be balanced by a force that is perpendicular to the member. Let's call this force V. And also dx and V produce a couple, which is a counterclockwise couple. So this has to be balanced also by a moment, which is a clockwise moment on member DE. And of course with an opposite sign on member ABC. So now we have three forces internally to this member. So we have the axial force, but then we have two more forces and moments. So let's recap. P is the axial force. It's the same as before as for straight to four members. It has the same physical meaning. And its effect on the member is that it elongates the member. It makes the member to become shorter or longer, depending on its sign. Then we have this force V perpendicular to the member. We call this force a shear force. And if you look at the effect of these two forces at E, in fact, it tends to cut the member like a scissors would do. Imagine the action of a scissors. So that's the action of the two forces V, opposite and parallel at the same point. And the internal moment, it's called a bending moment. And it's a moment like any other moment, but it's called bending simply because its effect is to bend, to bend the member, to try to curve the member through bending. So now we have these three forces inside the member, not just one, three internal forces, which are again the axial force, the shear force, and the bending moment. Very important. Multi-force members have axial force, shear force, and bending moment internally to them. Finally, we shall look at a particular case, which is a two-force member which is non-straight. So case A was dealing with straight two-force members. Case C, in this case, we will look at a non-straight two-force member, like this one here. So being a two-force member means there are no forces acting along the member, so along A, B, and BC. And the forces acting at the ends of the member, at A and C, line along the line that connects points A and C. We're going to cut the member at point D, an arbitrary point along the member, just to determine what is going inside the member. So drawing now the resulting free body diagrams. This is point A, B, and C. Then of course we have the force F at the ends. Now if we look at the equilibrium of member AD, the shorter one, the simpler one, it's probably easier if we resolve force F applied at A into its orthogonal components, one running along the member and the other one directed perpendicular to the member, like so. And now it's obvious that for equilibrium for member AD, we will have an axial force, P, balancing one of those components. Another force that is perpendicular to the member, balancing the second component. So that looks like a shear force. And now we have a couple made by the component and V. So then we have to add a moment as well. So there is a major difference, as you can see, between a straight and a non-straight two-force member. The former one has only axial force inside the member. The non-straight member has all three internal forces. So an axial force, P, a shear force, V, and the bending moment, M. So even though they are both two-force members, from an external point of view, they're similar, they're two-force members, but internally, the straight member again has only axial force only, whereas the non-straight two-force member has three internal forces. Again, the axial force, the shear force, and the bending moment. So from this point of view, the non-straight two-force member is actually similar to a multi-force member because it has the same three internal forces like the multi-force members do. So in the next lectures, we're going to see how we can determine these internal forces along a specific member which is called a beam. So thank you very much for watching this lecture, and I will see you shortly at the next ones.